In this lesson, we are going to take the percent by masses that we developed last lesson by using part over total. That's a laboratory technique, and we did an example of that laboratory technique of using percent by masses in the hydrate lab. We found the percent by mass of water in the hydrate, or you're going to do so very soon. So this technique of finding the actual percentage of the parts of a compound is used also not only to identify, but to figure out their empirical and eventually their molecular formulas. So empirical, as you guys may have talked about, is the lowest ratio. And this lowest ratio always comes from, at some point or other, percentages. Percentages help us get their ratios. What do you mean by percentages? Well, these are percent by mass. So we do labs or lab techniques that help us get the percent by mass of different compounds. The lab technique that we're studying right now is the hydrate lab. Now a hydrate, of course, is a salt. It's an ionic compound, and it has water, that's an and sign, and water locked in the crystal. That's what a hydrate is. To find the percent by mass of the water, what we did was we drove away the water and we were left by the salt. When you compare the two masses and do the part over total, we got that, or you're going to get that very soon in the lab. Now, how do we get the percent by mass of different compounds? For instance, in number 1 here, I have carbon and hydrogen in my compound. We don't know how many atoms are bonded to each to make the molecule of carbon and hydrogen. What we do know is when we analyzed it by a technique very similar to what we did to do the hydrate lab, we came up, all right, with percentages. And these percentages are, we got 14.3% of the entire mass of the compound we studied to be, okay, hydrogen. And we also got the percent for the carbon. So what we did probably in this type of technique is we probably took something with carbon and hydrogen and we drove off one or the other. Okay, and then we, by driving them off, we knew what was left and we had a percent, very similar to what we did with the hydrate lab. It's the same technique. Maybe we wouldn't use heat, but maybe we would have some kind of chemical reaction where we can force the H away and leave the carbon. And then knowing how much carbon there was and knowing how much we started with, we can do something very similar to what we did in the hydrate lab. But the techniques are very similar, and what they lead us to do, though, is from these percentages we should be able to build a chemical formula. That's what we're about today. We're building chemical formulas from the percentages, and the percentages come from laboratory techniques that are just like the one you did for the hydrate lab. So let's get started. Let's get rid of some of this and let's see what they gave us. Now they gave us some percentages, and these percentages again came from a laboratory scenario. So we've got 14.3% hydrogen atoms, or we would say 14.3% of the entire mass of the sample we're studying, and we don't know what it is. But we do know it's made of carbon and hydrogen. So out of this sample, okay, 14.3% of the entire mass is due to hydrogen. How did we get that? Maybe we drove away the carbon. What was left was a hydrogen. Just like driving away the water, what was left was the anhydrates. Some of the same things. Now, what we have is 85.7% carbon. That was also the other percentages. Notice when these add up, this should give us 100. So the entire mass of the sample is made up of two different atoms, and we have the percent by mass, just like we did yesterday. Now, how do we move a percent by mass into actual numbers of atoms that fit into the chemical formula? How do we do that? Well, the numbers that go in a formula, just like water, you know that there's 2 hydrogen atoms per 1 oxygen. How do we build a chemical formula? Well, we have to have a ratio. There's 2 H's per 1 oxygen. Somehow we have to move these percentages to a number that tells me how many atoms. My friends in chemistry, this right here is a percent by mass. It's not percent by how many. Okay, so somehow we have to move by percentages to a how many number, and I'm going to help you with that today. So how do we do that? Well, the first thing we're going to do is make these into grams. So the first thing, I'm going to make a donkey out of you and me, and we're going to assume. When you assume, we'll leave it at that. We're going to assume a 100-gram sample. Now, why can I assume a 100-gram sample? Well, because a percentage, my friends, is just really a fraction. If I have half the cake, I eat half the cake, but the cake can be any size. So I'm going to pick a 100-gram sample so that I know that 14.3% of 100, you guessed it, is 14.3 grams of hydrogen atoms. And 85.7% carbon out of 100, or 85.7% of 100, is of course 85.7 grams. Looky here. We made our percentages equal grams if we assumed a nice round number. Now again, this doesn't help me either because, well, these are still heavy. If every single element had the same mass, then we could use the percentages directly for these ratios. We have to convert these numbers now into how many numbers. We have to convert this how heavy, right, into how many. And the way that we do that is we are actually going to convert into something called moles. Now, it's not important that we quite understand the moles, but it's kind of like the formula in molecular mass we did yesterday. What is the formula mass of just hydrogen? Well, if you look on the periodic table, hydrogen has a mass of 1. And if we said the formula of hydrogen with one H is 1, well, we're going to make a leap and say, well, that 1 AMU is actually 1 gram. And 1 gram of hydrogen equals 1 mole. Now, what's a mole? A mole represents a number. Like a dozen is a word that represents 12. A mole is a number that represents a big number. And it's not important that we talk about that. What we're looking to do is come up with an equivalent. Okay? So 1 mole equals actually a number of molecules. Actually, it's a huge number, and it's not important to talk about it. But it's an equivalent, right? 1 gross, 1 bag, it could equal 3, 4. It's an equivalent. So we're going to convert this. Now, carbon, if you do the formula mass of just carbon, another word they use is called the atomic mass of carbon. We know it's 12 AMUs per one of them. And if we have a mole of them, they actually are 12 grams. So the atomic mass that you see in your periodic table, it's the top number, that is also how many grams per some equivalent number called a mole. That equivalent is some number. Like if I had a dozen, we know it equals 12, but I don't have to keep saying it equals 12. I have 1 dozen. And if I have 1 dozen compared to what? 2 dozen, isn't that a 1 to 2 ratio? I don't care that this is really 12 and this is 24. Isn't it really a 12 to 24, a 1 to 2 ratio? So when I use the word mole, it represents some number. But notice it's the same number for both. So no matter if I'm using the actual number or the reduced word, which is 1 for a dozen, 2 for 2 dozen, it's not going to matter. So we're going to do more of this as the unit goes on. But really what you're giving me, this bottom number, you're getting from the what? You're getting from the formula. Since the formula is just an element, it's just the atomic mass of the element. So it's not a big stretch for what we've been doing. It's just that the formula mass now is just a mass of the what? The element symbol. Okay? And we're going to make that equal into grams. All right. Let's go find these moles which represent some equivalent value. These are both what? These are both 1 apiece, like 1 dozen apiece. Let's go see if we can come up with a ratio. So 4.3 divided by 1, okay, if you know your numbers here, forget that. All right, so that I get 14.3 moles. Don't get lost with the word moles. It could mean dozen of them. If you want to use dozen, I could care less. So this is mole, which is an equivalent. All right, if you're cool, you put the E, we'll leave the E there. I just used the abbreviated form. And then now we're going to convert our carbon atoms into moles. All right, this is grams of carbon into moles, I should say. And I take my 85.7 and I divide by 12, and that gives me 7.14. And that's moles of carbon. And just like we did, or At this point, we have dozens or moles. Is there a ratio? Can you look at the ratio here? There should be a whole number ratio lurking in our answer. Wait a minute, isn't 14.3 about twice of 7.4? So what we do at this point, we divide by the smallest number. The smallest number is going to be our 1, so we're going to divide by 7.14 mole. This gives me 1, and this gives me divide by 7.14. So we take our moles and we divide by the smallest number because we want the smallest number to be our smallest value. Okay, and that comes up with ratios. And if you want the exact number, 14.3 divide by 7.14, and what you get is 2.003, which is essentially about 2. Okay, now why is there a little bit here? Because of rounding. So we got a 2-to-1 ratio. Look at that. We went from what? Percent by mass into grams. We went from a heavy number into what? A how many number? Into dozens. Using the what? Using the atomic mass of the elements, just like we did yesterday with the formula mass. We used all the individual atoms, like when it was NaCl, or we added all the atoms together. So in any case, I got a 2-to-1 ratio. Let's look at that. What does that mean? Well, that means I have a carbon and I have a hydrogen. And looky here. There are 2 hydrogens. Look at that ratio, 2 right there, for every 1 carbon. You don't have to put the 1 there, it's implied. Kind of like having an apple. You don't have to say I have 1 apple in my hand, you have an apple. So we get rid of that 1 there. Alrighty. And there, my friends, is something called an empirical formula. That's the lowest ratio. It's a 1-to-2 ratio. And that's the empirical formula. That's the answer. Now, as you probably have learned, empirical formulas aren't exactly how a lot of molecules exist in nature, although there can be some that do so. How do I know? Well, carbon has 4 valence electrons. Hydrogen has 1. So if you bring these to the table, clearly, if you do your Lewis dot diagram, carbon's not going to be stable. It doesn't have its octet. This does not exist in nature this way. So I want you to understand that empirical formulas are the lowest ratio, and we always get a lowest ratio when we start with a percentage, right? If you're starting with a percentage, you can only get these lowest ratios. We don't know exactly how the actual bond, but we just get the lowest ratio. And what we do with the lowest ratio, with another laboratory technique that will give us the molecular formula, we can actually find what this is. So, given the CH2 as our lowest ratio, called the empirical, we're going to try to find the molecular. Now, the molecular formula is how it exists in nature. How does it actually bond in nature? Clearly, CH2 does not exist in nature because carbon needs, what, 2 more electrons to make this work. We know that CH4 works, but not CH2. So here's how I do this. In this question, they're giving you the molecular mass. This molecular mass is equal to 28. So what's going on here? Well, they did another laboratory technique with another piece of the same sample, and they came up with the molecular mass. The mass per, guess what? 1 mole. And they found it to be 28. By the way, that's called a formula mass if you're dealing with ionic compounds. Okay, so here's how I do this. I call it a box question, and you could certainly do this many different ways. What I do is I put the empirical, the lowest ratio formula on the bottom. We're trying to come up with the actual formula called the molecular formula. They gave me the mass of the molecular formula to be 28. Okay, so this is my molecular formula on top, which is, guess what, usually a whole number multiple, and my empirical formula on the bottom, which is the lowest whole number. So my friends, that's why I put CH2 in the bottom. It's the lowest whole number. So what I'm going to do now is find the mass of CH2. Okay, just stay with me for a second if you don't quite understand. I have 1 carbon, which is 12, right? 1 carbon, 1 times 12 is 12. I have 2 H's, 2 times 1, no, my 1 times tables is 2. I get a total mass of my empirical formula to be 14. Hello, look at this, 28. Isn't this twice that number? Hello. So therefore, hello, this is twice, oops, this is twice that value. So what's 2 times H? C2. What's 2 times H2? H4. You just found the molecular formula. Right? We were given we figured out the empirical. I found the empirical mass. I saw that the molecular formula was a whole number multiple. And that's what molecular formulas are. They're usually whole number multiples. This will always be a whole number. Case in point, if I give you hydrogen peroxide exists in nature as H2O2. This is exactly how this particle or molecule bonds. That's its molecular formula. If we were to do the empirical analysis laboratory technique, this would reduce down to you guessed it, a HO, which could be the lowest denominator of things. I'm not sure. But the bottom line is the HO, or HO, is the empirical formula, the lowest ratio. This is what we would come up with in lab using percentages, because percentages always lead to whole number ratios. And loaded with the molecular mass, we can actually get this value. All right? So what I'd like you to do right now is I'd like you to do number 2 right now. Teacher, whoever's in here, please pause me, all right? Or I'll start reciting some poem that you won't like. Please stop me right now, and you guys do number 2, and when you bring me back, we'll see if your answer matches mine. If you're kind of lost, okay, look at my work, okay? Pause me right here and see what I did to get this, okay? And what I start with. I took my percentages, okay, yeah, just pause me, look at my work and see what I did here. And try number 2. If you're having problems, I will review number 2 in its entirety. Okay, I am back, and let's see what I got compared to what you have. So in number 2, I was given the percentages of each of these elements per mass. Okay, so I got 39.7% sodium. That's what I have here. And I have 60.3% chlorine. And the first step is I assume a 100-gram sample. And when I do so, my percentages become grams exactly, because I'm using 39.7% of 100 is exactly that number. I can assume a 200-gram sample, but then I have to do the work. It'd be twice as much. Just assume a 100-gram sample, and the percentages become exactly the grams. Now, once we are in these grams, we have to convert this how heavy number into a how many number. We're going to convert grams into a number. A mole represents some number, just like a dozen does. So what we do to convert that is we use the atomic mass of the chemical. Sodium has an atomic mass of 23 when you round off. Atomic number is 11. We're getting this from the periodic table. Okay, I'm not showing you now anymore because they're all grown up now and ready to do this. Okay, so same thing with chlorine. We convert to moles, but notice it's got a different mass number. Chlorine is 35.4. I rounded to 35. And then I found that I have this number of moles, which could be like dozens. It doesn't matter. It's an equivalent. The bottom line is that these numbers are essentially the same, but what do we do in this scenario? We divide by the smallest number all the way through. To get a ratio, the smallest number, for it to be 1, we divide by the smallest number. And if you're still confused about that, think about people in this room. Think about me. I generally am a little more taller than some people. So if we wanted to have a ratio of my height to someone else's height, I would start with the shortest person. No offense, okay? But I would make this the standard, divide this by itself, it's a 1, this would be like 1.2, and maybe the smallest person to me, this would have a ratio of 2. So that's how we do that. And once we have their ratios, which in this case you can clearly see they're about the same. They're not going to be perfect, but you can round to them. And the reason why they're perfect is because of rounding, but they're essentially the same, which means we have a 1-to-1 ratio of chlorine to sodium. And we've just built our empirical formula, which, by the way, is exactly how sodium exists in nature. Unlike CH2, okay, this is a molecular compound. It needs to have a molecular formula that makes sense. Something that's ionic, okay, like NaCl, you will come up with exactly its chemical formula, because you guys know when you have ionic compounds, you have to reduce to the lowest number of ions. These do not make crystals. These make what? Crystal lattices that go in all directions, that keep going. When you have NaCl, it means you have a 1-to-1 ratio of positive ions to negative ions in your crystal. Okay, we do not write molecular formulas for ionic compounds. And you may say, well, why don't I? Well, I don't, because can sodium, would you write NaCl, Na2Cl? That would mean you have a crystal that's 4 ions total. We don't do that. You crisscross. Remember, when you build sodium chloride, you take the positive one, you take the Cl negative one, and what do? You crisscross and you reduce the lowest terms. This never makes any sense for things that are ionic. Okay? So that's how we do those problems. We're building chemical formulas of compounds by finding the lowest whole numbers. And if we have the molecular mass, we would do the box question. So the rest of these questions, number 3, is the box question. I'll walk you through one more, and the rest will be on your own. Number 3 is a question where I give you already the empirical formula that they must have figured out by the technique that we just did. Using a laboratory technique that gets the percentages and using this math, they came up with CH3. So I write my box, I write my lowest ratio on the bottom, which is the empirical, because it is the lowest denominator. I put my molecular mass as 30. The next step, what do? I find the empirical mass. One carbon is 12 from the periodic table, and each hydrogen is 1 apiece from the periodic table. And this gives me 15 grams per mole. Look at this. It's a whole number multiple. I times that by 2. Wow, I times that by 2. C2H6. And what you can do, party people, is you can see if this equals this if you add it together real fast. 2 times 12, right, because there's 2 carbons, is 24. And each H is 6, so you add 6 and you would get 30. So that's going to equal each other, and that's your answer. So please, on your own, do 4, 5, 6, and 7. Do 4, 5, and 6, and stop me. Stop me now and see what you get. So I'm back, and here we are with our, I think, 3 in a row questions here. Number 4, you should have gotten N2O5, which is strange. We started with N2O5. How did we get back with N2O5? Well, my friends in chemistry, there are chemicals that are already in their lowest ratio, and they exist that way in nature, and N2O5 is one of those. So here's an example where N2O5 is both an empirical and a molecular when you did your math. Notice I have the math done over here that shows me the empirical mass, and then the molecular mass they give me is 108, and that's a factor of 1 or the same. Okay, H2O is a molecular form. H2O exists as 2 hydrogens to 1 oxygen, and that's already its lowest ratio, and water exists that way. Number 5, your answer is C6H6. Given CH, finding the empirical mass of CH, I get 13. And I know that 78 is what they give me. 78 divided by 13 is 6, or 6 times 13 is 78. So I times this by 6. Notice it's the same value. Multiply this by 6. I times this by 6. 6 times 1 is 6 C's. 6 times 8 is 6 H's. And number 6, okay, you should get C4H8 for the same reasoning. This should be easy. This should be easy. Okay, so let's get to number 7 or 8. So number 7 and number 8 are very important questions, and if you haven't already guessed it, this is going to be your next lab. We're going to build the chemical formula of a hydrate, and you're going to do it experimentally. Okay, and how do you do that? Well, you would do an experiment where we take the hydrate, we would heat it, drive the water off, and you'd have the anhydrate mass. Notice they have the mass of the hydrate, and they have the mass of the anhydrate. And then you would find the percent by water. And then if you knew the percent by water, you know the percent by the dried compound. So we're going to jump down to number 8. Number 7 is going to be either your homework or classwork. I'm going to show you how to do it with number 8. Now with number 7, you have the grams of the hydrate and anhydrate already. And from the questions that we did yesterday, given the anhydrate value and given the hydrate value, you should be able to generate a percent by mass of the hydrate just using those two values. If you don't know, revisit my lecture 1 of this week. Okay, so we're going to jump down to number 8, where I've already done the lab, meaning I already got the grams of the water. I already got the grams of the anhydrate. Okay, and from the grams of those, I converted to percentages. Okay, now, kind of silly for me to go backwards, but what we do is by having the percentages already, I'm going to convert them to grams. And I say it's silly because if you have the grams of these from the experiment, you don't have to go to percentages and then back to grams. That's why number 7 is in grams already. And if you're in grams, you would go directly into, guess what, moles. Then do a mole ratio, divide by the smallest one, and then see a ratio. But in this case, they gave me the percentages. So just like we did before, we'll take our 45.43%. Now this is a little different because we're not dealing with individual elements. This is the hydrate's 45.43 water. So this is the water. So we don't write hydrogen or oxygen, it's the entire water. This is 54.57 anhydrate. This is cobalt 2 chloride. Now cobalt is +2 because of the Roman numeral. Chloride tells me it's binary, it's just a Cl, and it's -1. So when I crisscross, okay, you can clearly see I need 2 chlorines for 1 cobalt. That's something we should have down now at this point. Okay, this is the +2 cobalt. So this is the anhydrate. Now if you don't know what you're doing here, here's the hydrate. We have cobalt, we have chloride, we've got a dot, and we have some number of waters in our formula. We're trying to figure out what that number is. What's the ratio of water molecules to this, if you want to call it a particle? So the first step is to convert, as you've noticed, to moles, or a number that tells me how many. Now that would be correct if in fact I was in grams already. So what I'm going to first do, as you probably have corrected me, and we all make mistakes, is assume a 100-gram sample. We're going to make a donkey out of you and me. Now once we've made those donkeys, we have 45.43 grams, and then we have 54.57 grams. It's a nice little conversion. Percentages right to grams if we have a 100-gram sample. Now the next step is to convert this into a how many number, like a dozen. That's what a mole is, a word that describes a number. And we know that that equivalent number is equal to the what? The formula mass that we've been working on. So the formula mass of H2O is 18 grams. How do I know that? I've been doing that a while, but very simply we have a 16 for the oxygen, right? Oxygen is 116, and then we have the 2 hydrogens. 2 times 1 is 2. Add the 16 and 2 together. That's how I got my 18. The next step is I have to convert this into a how many number, the mole, and I got to find the formula mass of cobalt chloride. So I have to go to my periodic table. And there's cobalt, 58.9, so I can use that AMU, atomic mass unit, also as grams per 1 mole. So 58.9, we'll round to 59. Okay, and get rid of this. And so 1 cobalt, 1 times 59, and by 1 times tables it's 59. Then I have 2 chlorines, and from the reference table, each one is 35.4. I round to 35. and I get 70. The tire mass is 9, 7 2 is 12, 129 grams per 1 mole. Why is this number so much bigger? Because there's more atoms, especially this one's heavier. Okay, so let's go find those moles with our calculator. So 45.43 divide by 18 helps to turn the calculator on. 45.43 divided by 18 equals 2.52, and then 54.57 divided by 129 is 0.423. Now, of course, these numbers do not go into the formula. We need whole number ratios, so we divide by the smallest number. The smallest number is 0.423, and 2.52 divided by 4.23 gives me 5.95. 5.95 you can round to 6, and this divided by 0.423 is equal to, I don't know, I'll do it. Oh, of course it's equal to 1 times divide by itself. So that means I have what? 6 waters. That becomes a 6 for every 1 what? Anhydrate. One of these is 1. So the chemical formula, party people, is COCl2 dot 6 H2Os. That's your answer. Okay, so try number 7. If you have time in class, do that for homework. Thank you.